All right, one of the next things to talk about is what's called change of basis. And so the idea here is that if I were to take any vector, let's just start with R2. Okay, so let's pick an actual concrete vector in R2, say 3, -1. And so if I were to pick this vector 3, -1 in the standard coordinate system, what this would be the vector where what it's going to do is it's going to map the origin to the point 3, -1. Okay, so say something like that. And so it's going to be this vector. Okay, it's going to map the origin of the point 3, -1. And what we can do is we can think of this as a linear combination of, well, let's just write it this way. 3, -1, we can write as 3 times the vector 1, 0, plus -1 times the vector 0, 1, where 1, 0, and 0, 1 are the standard basis vectors. Usually we call this I and j, or I hat and j hat. Okay, so those are the standard basis vectors. And so we can think of this as a linear combination of, let's say I have I, which is the unit length, unit vector in the x direction, and j, okay, which is, say, here. And so we can scale I by a factor of 3. That would make it there. Scale j by a factor of -1. That flips it. And then if we were to take this scaled vector, so 3i minus j, and add those together, that really means that you just put them tip to tail. You end up with this new vector, right? So you end up with 3, -1. So this is all old news. This is just writing a vector is a linear combination of these standard basis vectors. And it turns out that we can actually do this for any basis. So the first thing I want to do is, let's say I have a new basis. Let's say I have a new basis for R2. Let's say 2, let's say 2, 1, 5, 3. I know that this is a basis for R2, by the way, because if I were to look at the determinant of 2, 1, 5, 3, that's non-zero. That means that these column vectors are going to span all of R2, and they're linearly independent, right? Things that we've talked about. So the determinant being non-zero, again, the determinant tells you quite a bit of information about that matrix, and in particular, in this case, about the columns of the matrix. So let's say B prime is this basis for R2. What I want to do is I want to think about, how do we mimic what happened above, right? How do I find these constants so that I can write this vector, 3, -1, as a linear combination of our two basis vectors? So what I really want to do is I want to find values of C and D so that I can write our basis, our vector 3, -1 is a linear combination of our two basis vectors, 2, 1, and 5, 3. Okay, once I find those values of C and D, what I can do is I can write the vector 3, -1 as the vector CD relative to the basis B prime. So if I don't have any subscript here, which is what we're used to seeing, this is where we started, then we're talking about our standard basis. So 3, -1 we can write as 3 plus -1. So it's a linear combination in that way of our basis vectors. Okay? And so I want to find values of C and D so that we can write it like this. And it turns out, if you think about all that we've talked about for solving systems, this is really just a system with two equations and two unknowns. You can write it as a matrix, and it turns out that we're going to write it like this. So we have 3, -1 this is going to be equal to, you can just check that these are equal on your own, but this is equal to the matrix 2, 5, 1, 3 times CD, right? And so if you were to go backwards, if you were to multiply these two matrices, you would get 2C plus 5D, which is what you get here. And then down here you get 1C plus 3D, which is again what you get there. That's equal to 3 and negative 1. Okay, so really this is just a new way to write that system, okay, to write it as a matrix. But the reason why we want to do that is that what we can do is we can solve, just algebraically doing matrix algebra, we can solve for CD, right? CD is going to be equal to, let's see, if I were to multiply both sides by the inverse of this matrix on the left, what we would end up with would be whatever this inverse is, we'll figure that out in a second, times 3, negative 1. That would be how we would write this for C and D, okay? And how do I know that this matrix has an inverse? Well, we said before the determinant's non-zero, right? Because it's the columns of that matrix form a basis for R2. So we know that the determinant's non-zero, therefore it has an inverse. Everything works perfectly well together. And then for actually computing this inverse, remember that when you compute the inverse of a 2 by 2 matrix, we know how to do that. What we do is we flip the role of the main diagonal, so 2 and 3. So those get flipped. And then we make the off diagonals negative, and then we have to divide by the determinant, except that the determinant is 1. Okay, so if we're going to divide, I mean it's 6 minus 5, so we're going to divide everything by 1, but we don't really need to write that. And so we're ready to say that CD is going to be, let's see, we have 3 times 3 is 9 plus 5, so 14, and negative 3 minus 2, so 14 and negative 5. And so it turns out that if I were to write the vector 3, negative 1, using our standard basis, I could also write that as the vector 14, comma, minus 5, relative to the basis B prime, where again B prime was the basis consisting of the vectors 2, 1 and 5, 3. Okay, so this is just another way to write a vector relative to this basis. Switching coordinate systems seems a little bit silly because it seems like most of the things that we want to do should work for the standard coordinate system, except it turns out that there's lots of reasons why we would want to do this. Lots of places, really. So we'll talk about some applications specifically in Chapter 7 when we talk about diagonalization of matrices. So we'll talk about what that means later, but there's some good reasons why we would want to do this. So I could repeat this in general. I think it's worth just saying a few more things here. I could repeat this in general. So in general, if I have the vector AB relative to the standard basis, I could write that as, so I'm just going to copy what I did up here. This is really 2, 5, 1, 3 times CD. In other words, CD is going to be the inverse matrix, which we said was 3, negative 5, negative 1, 2, times AB. And I can do that for any vector AB that I want. Okay, so there's a change of basis there. Let's do this. I want to do 2 more things here in this video. Let's do this again for a second basis now that we've seen this story, just to see kind of how it works in general. So we have, say, 0, 2, and 1, 6. And so if I have 0, 2, and 1, 6, what I want to do is I want to pick some vector AB in the standard basis in R2, and I want to write it relative to the basis B double prime. So in other words, I want to find these constants C and D so that I can write this relative to the basis B double prime. And so what that means is that we really want to find C and D so that we really want to find values of C and D so that the quantity A times B is equal to 0.216 CD. And so really that means CD is going to be the inverse of this matrix 0, 1, 2, 6. This is a matrix with a determinant of -2. So I'm going to divide by -2 times AB. And let's see, if I switch the role of the main diagonals and make the off diagonals negative, there we go, there's our inverse. So our inverse is going to end up being, let's see, -3, +1/2, +1, 0. Okay, so there's our matrix transformation there. And so I could, again, take 3, -1, and I could write it, let's see, if A is 3, right, so this is -3, 1/2, 1, 0. So if A was 3, and we have to be double primes here. I want to be consistent with my notation here. But if A was 3 and B was -1, then what we'll get when we take this product would be -9 minus 1/2, so that's -19 halves. And if A is 3 and B is -1, then we're going to get, let's see, 3 times 1 plus 0, so 3. And so that's how we would write those two. We would write this vector 3, -1 relative to the standard basis B, relative to the basis B prime that we did above, and relative to this basis B double prime. And so now the question is, what I really want to know, and really what the content of this entire section is about, is the following. So we have our three bases. We have our standard basis, B, which is 1, 0, 0, 1. We have our basis, B prime. B prime was, so the basis B prime was 2, 1, 5, 3. And then we had B double prime, which we can see above was 0, 2, 1, 6. Okay, and so we've talked about how do we go back and forth between B and B prime and B double prime. But what I really want to talk about is what's called a change of basis formula. And so that's how do you go between any two bases. And it turns out that the way that I want to motivate this, the way that I want to think about this, is that if I want to go from B prime to B double prime, what I could do is I could go from B prime to B, and then from B to B double prime. Okay, and so that's the way that I really want to think about this. And so let's just recap here. I know that we just did this in the same video, but I think it's worth just recapping just because I want to use slightly different language now. Okay, but previously what we did is we took some arbitrary vector AB in R2 according to the standard relative basis. So this is the usual vector AB. And we wanted to write this as a linear combination of the basis vectors in B prime. So we had 2, 1, 5, 3. This, by the way, is a 5, 3, though. it didn't show up very well on the screen. So 2153 times CD. And this CD, by the way, was relative to the basis B prime. So, yeah, so what we wanted to do was we wanted to write AB in this form. And so let's just say that this is, let's just call this matrix M. Okay, times CD. Okay, and again, there's kind of a hidden B prime here. So if you want to write it that way, that's fine. And so AB is going to be M times this vector CD. And this is CD relative to the basis B prime. And likewise, if we had AB, we had our other basis was 0, 1, 2, 6. That was our matrix, so the vector 0, 2, and 1, 6 as our columns. And what I want to do is I'm going to write this as E and F relative to the basis B double prime. And so let's call that matrix A. So AB is equal to A times EF relative to the basis B double prime. And again, I want to just figure out how to go from one to the other. Okay, say from B prime to B double prime. It doesn't really matter which direction we go. So if we have a formula to go from one basis to the other, then it's got to be true in reverse. So since these are both equal to the vector AB, that means that they must actually be equal to each other. So this implies that M, the matrix M times CD relative to B prime is equal to A times the vector EF relative to the basis B double prime. And therefore, if I were to write EF relative to B double prime, what I could do is I would take A and move it over, except I would get A inverse, right? We would just multiply both sides by A inverse. So we get A inverse times M CD. Okay, and so this is our entire change of basis formula. And again, the idea is if I want to go from B prime to B double prime, what I do is I go first from B prime to B. So if M is the matrix that we use to go from B to B prime, then that means that M inverse, moving that over, M inverse is the matrix that we use to go I want to go from B prime to B. So M is our matrix there. Did I do this slightly? Let's see. No, everything's fine. So so first we apply the transformation to get from B prime to B, and then from B to B double prime. Okay, and we end up with our formula there. There's our change of basis formula.